So students, now we'll discuss relation on a set. Okay, this is relation on a set. In previous case, we have discussed relation defined on set A to B. Okay, if A is equal to B, where A is a non-empty set, okay, and A equal to B, then a relation from A to A, because A is B, so relation from A to B is same as relation from A to A, is called relation on set A. That is, here A cross B is same as A into A, and R is a subset of A into A. So any subset of A into A is relation on A. Okay. Now we discuss inverse of a relation. So here we can give an example of a relation on a set A. Suppose students, suppose A equal to 1, 2, 3, 4, and this equal to B. We have A into B is same as A into A because A equal to B, which is equal to order pair AB such that A, B both belong to A. So A cross A. So A cross A contain element like 1, 1, 1, 2, 1, 3, okay, 1, 4, 2, 1, 2, 2, 2, 3, 2, 4, 3, 1, 3, 2, 3, 3, 3, 4, 4, 1, 4, 2, 4, 3, 4, 4. Okay, now R is a subset of A into A. Suppose R equal to order pair xy such that x plus y equal to 5. So now this relation R equal to, it is 1, 4, 2, 3, 3, 2, 4, 1. Okay. So these are the element of order pair xy so that x plus y equal to 5. So R is this relation. Here R is a subset of A into A. So here R is a relation on A. Here R is a relation on A. We can say that because A equal to same as B. So we say that R is a relation on A. Okay. Now we'll discuss inverse of a relation. Let A be two set and R be a relation from set A to set B. Then the inverse of R is denoted by R inverse is a relation from B to A and is defined by R inverse equal to order pair BA such that AB belongs to R. Clearly, if AB belongs to R, then BA belongs to R inverse. Okay, so we'll define an example of inverse of a relation here. Suppose R equal to suppose R equal to 1, 2, 3, 4, 5, 6. Okay, suppose A is 1, 3, 5, B is 2, 4, 6, 8 like that. R is 1, 2, 3, 4, 5, 6. Now R inverse equal to the reverse of order pair. If AB is in R, then BA is in R inverse. So 2, 1, 4, 3, 6, 5. Okay, this is R inverse. Clear? Now we'll discuss type of relation. First is void or empty relation. Sometimes it is called null relation as well. Let A be a set, then and B is also another set. Now, any subset of A cross B is a relation. Since phi is a subset of A cross B, phi is an empty set. Empty set is a subset of every set. So phi is a subset of A into B. Okay. So phi is a relation. So it is a relation on A into B. If B equal to A, if A equal to B, then phi is a relation on A. This relation is called void relation or empty relation on set A. Okay. Now universal relation. Let A be a set, then A cross B is subset of A cross B. In every set is a subset of itself. So A cross B is a subset of A cross B. So it is a relation on A. So it is a relation on A. Any subset of itself is a relation. Any subset of A cross B is a relation. So A cross B is also a relation. That is called universal relation on set A. On set A if A equal to B. Okay, if A equal to B, then A into A is same as A into B. Okay, any subset of A into A is a relation. So A into A is a subset of A into A. So A into A is a relation. That relation is called universal relation on set A. Okay. Now we'll give an example of uh, void relation and universal relation. Suppose A equal to B equal to 1, 2, 3. Okay. Then R is a subset of A into B, where A into B contain 9 elements 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, 3, 1, 3, 2, 3, 3. Okay. So A into B contain 9 elements. R should be contain few element of them. Suppose sometime R contain none of the element of A into B. Sometime R contain all the element of A into B. And in this case, when R contain all the element of A into B or A cross B, okay, or A cross product B, then in this case R is called universal relation. If R contain no element of A cross B, then it is called void relation or empty relation. For example, here we define R equal to order pair xy such that x plus y equal to 6. Here x plus y equal to 7, suppose. X plus y equal to 7. So here you see 1 plus 1 is 2, 1 plus 2, 3, 1 plus 3, 4, 2 plus 1, 3, 2 plus 2, 4, 2 plus 3, 5, 3 plus 1, 4, 3 plus 2, 5, 3 plus 3, 6. Okay. So there is no element, no order pair xy is there, so that x plus y equals 7. So it contains no element. This is 5. So it is an empty relation or void relation. Okay. Now we'll take another relation. Suppose this is R star and this is R double star. Or you can write R1 or R2 as well. R double star equal to order pair xy such that x plus y is greater than 2. Then it contain x plus y greater than 2. Then it contain element like greater than equal to 2. So it all contain all element 1 plus 1, 2, 1 plus 2, 3, 1 plus 3, 4, 2 plus 1, 3, 4, 5, 4, 5, 6. So it contain all element. Okay. So R star is a R star is same as A cross B. So R double star is same as A cross B. R double star is called universal relation. Okay, R double star is called as universal relation. Okay, so R star equal to this R star is empty relation. R double star is a universal relation. If since A equal to B, we can say that this is a empty relation on A. Again, R double star is a universal relation on A. Okay. Now we'll discuss about identity relation. Let A be a set, then the relation IA equal to A such that A belongs to A on A is called the identity relation on A. Let A equal to 1, 2, 3. Let the relation R given by R equal to 1, 1, 2, 2, 3, 3 is an identity relation. Okay. You see, A contain element 1, 2, 3. So 1, 1, 2, 2, 3, 3 is an identity relation because it contain all element of A 1, 1, 2, 2, 3, 3. Okay. It cannot contain any more extra element. Then it's called identity relation. Okay. You can give another example of identity relation here. Okay. Suppose A equal to 1, 2, 3, 4. Then identity relation is defined as 1, 1, 2, 2, 3, 3, 4, 4. So every element of A is related with itself. then it is called identity relation. Okay, that is image of, suppose this is A, this is also same as A. So here one A is 1, 2, 3, 4. Here also 1, 2, 3, 4. So image of 1 is 1, image of 2 is 2, image of 3 is 3, image of 4 is 4. That is 1 is related with 1, 2 is related with 2, 3 is related with 3, 4 is related with 4. Okay. So it is a identity relation. Understand, students? Now, if R1 is another relation defined by R1 equal to 1, 1, 2, 2, 3, 3, 1, 2, 2, 3, it is not an identity relation on the set A equal to 1, 2, 3, because A contains 3 element 1, 2, 3. Since 1, 1, 2, 2, 3, 3 is there, but it contains more extra element. So it is not an identity element. Okay. If these two elements are removed, then it become a identity relation. Now reflexive relation. A relation on a set A is said to be reflexive if every element of A is related to itself. Thus R is reflexive, that implies A belongs to R for all A belongs to R. Note, every identity relation is reflexive but the converse is not. Students, ଏଠି ଗୋଟେ କନଫ୍ୟୁଜନ ଆସେ ଯେ ରିଲେଟିଭ ରିଫ୍ଲେକ୍ସିଭ ରିଲେସନ କଣ ଆଉ ଆଇଡେଣ୍ଟି ରିଲେସନ କଣ, ତାଙ୍କର ତ ଡିଫରେନ୍ସ କଣ? We'll understand this with the help of one example. What is the difference between identity relation and reflexive relation? Suppose A equal to 1, 2, 3, and we have a relation like 1, 1, 2, 2, 3, 3 only. Okay, so it is a identity relation. Every identity relation is also reflexive. This is also reflexive relation. This is also reflexive relation because A belongs to the relation or all A belongs to A. Now, suppose we have a relation like this 1, 1, 2, 2, 3, 3, 1, 2, 2, 1. Since 1, 1, 2, 2, 3, 3, 1, 1, 2, 2, 3, 3 all are present here. Okay, except that we have extra element. Except that if you have extra element, then that element, that relation is reflexive relation. It is reflexive relation, but it is not identity. It is not identity. Okay. If note, you can write in the note, if extra element is there, if extra element is there, except identity element, except identity element, that is 1, 1, image of 1 is 1, image of 2 is 2, image of 3 is 3, except that if extra element is there, then it is called reflexive, then it is called reflexive. Okay, so in case of reflexive, some extra element is there. In case of identity, there is no extra element is there, only 1, 1, 2, 2, 3, 3, only identity element are there. Okay, that means only identity mappings elements are there. Okay, hope you understand clearly. Now, let A equal to 1, 2, 3 and the relation R given by R equal to 1, 1, 2, 2, 3, 3. It is an identity as well as reflexive relation. If R1 is another relation defined by R1 equal to 1, 1, 2, 2, 3, 3, 1, 2, 2, 3 is not an identity relation, but it is only reflexive since 1, 1, 2, 2, 3, 3 is there. It is but extra element is there. Just previously I explained. Because of this extra element, it is not identity, but it is only reflexive. Now, symmetry relation. A relation R on a set A is said to be a symmetry relation. If AB belongs to R, that implies BA belongs to R for all AB belongs to A. So for AB belongs to R, that implies BA belongs to R. Then we say that relation is symmetric. For example, A equal to 1, 2, 3, 4, and the relation R given by R equal to 1, 1, 2, 3, 3, 2, 3, 4, 4, 3. This is a symmetric relation. You can see the reverse of 1, 1 is 1, 1. Reverse of 2, 3 is 3, 2. Reverse of 3, 4 is 4, 3. So for every AB belongs to R, there is a BA belongs to R. So it is a symmetric relation. Okay. Now we'll discuss transitive relation. Let A be any set. A relation R on A is said to be a transitive relation if AB belongs to R and BC belongs to R. That implies SC belongs to R. For all ABC belongs to A. That is A related to B related to C, then A related to C. For all ABC belongs to A. Then we say that the relation is transitive relation. Okay. Let A equal to 1, 2, 3, 4. Let R be the relation given by R equal to 1, 1, 2, 2, 3, 3, 4, 4, 2, 3, 3, 2, 3, 4, 4, 3, 4, 2. It is a transitive relation. You can combine 1, 1 with, you cannot combine with 1, 1 with anyone. So it is okay. 2, 2, 2, 3 is 2, 3. 2, 3, 3, 2 is 2, 2. 3, 2, 2, 3 is 3, 3. 4, 3, 3, 4 is 4, 4. Okay. So 4, 2, 2, 3 is 4, 3. So for every belongs to R, BC belongs to R, we have AC belongs to R. So it is a transitive relation. Okay. You can create more example by yourself. Okay. Now, students, here we'll discuss some real life example of reflexive. Okay. Some real life example of reflexive, symmetric, and transitive. Reflexive, symmetric, and transitive. Suppose, suppose you take friendship relation. Everybody is a friendship of itself. So friendship is a reflexive relation. Okay. Now friendship. If A is friend of B, then B is friend of A. If Ram is friend of Hari, then Hari is friend of Ram. So friendship is a symmetric relation. But friendship is not transitive. Suppose Ram is friend of Hari, but Hari have another friend in his village or in Hari have another Facebook friends that Rama does not know. So friendship relation is not transitive. But friendship relation in a class. Friendship relation in a class. Okay. So in a class, every student is friend of itself. So if X is friend of Y, Y is friend of Z, then X is friend of Z. So in class, friendship relation is transitive. Now brother relation. What about brother? Suppose brother relation. Everyone is a brother of itself? No. So brother relation is not reflexive. Ram is brother of Hari, then Hari is brother of Ram. So brother relation is symmetric. Okay. Now whether brother relation is transitive or not? Yes. If Ram is brother of Hari, Hari is brother of Sam, then Ram is brother of Sam. So it is transitive. Brother relation is transitive. Okay. So similarly, you can make more example, more real life example as well as mathematical example. Okay. To understand the topic, the reflexive relation, symmetric relation, and transitive relation. So students, now we'll discuss another important type of relation. That relation is called equivalence relation. A relation R on a set A is said to be an equivalence relation on A if and only if it is reflexive, symmetric, transitive. If a relation is reflexive, symmetric, and transitive, then it is called equivalence relation. That is A belongs to R for all A belongs to A. That is AB belongs to R for all. That is AB belongs to R. That implies BA belongs to R for all AB belongs to A. Transitive, that is AB belongs to R and BC belongs to R. That implies SC belongs to R for all ABC belongs to A. So it is reflexive, symmetric, and transitive. Okay. So a relation on set A is said to be equivalence relation if it is reflexive, symmetric, and transitive. For example, suppose A equal to 1, 2, 3, 4, and let the relation R given by R equal to 1, 1, 2, 2, 3, 3, 4, 4, 2, 3, 3, 2, 3, 4, 4, 3, 4, 2, 2, 4. Now you see, for every element of A, we have A belongs to A, so it is reflexive. Now for every order pair AP, we have PA for 2, 3, 3, 2, for 3, 4, 4, 3, for 4, 2, 2, 4 is there. Now you can see for AP, for every AP belongs to R, BC belongs to R, AC also belongs to R. So it is transitive. So this is a equivalence relation because it is reflexive, symmetric, and transitive. Now, equivalence class. It is very important thing, students, in our syllabus. Equivalence class. What is equivalence class? Every equivalence relation defined on a set divide the set into pairwise disjoint subsets called equivalence classes, whose collection is called a partition of the set. That is, by the equivalence relation, a set A can be separated as can be partitioned the set. Okay, so that union of all equivalence classes is the whole set. Okay, and the intersection of two equivalent classes may be the phi or maybe the same set. Two equivalence classes are either equal or they are disjoint. Okay, the equivalence class contain A, that is a set of element related to A under the relation R is denoted by equivalence class of R. Equivalence class contain A, that is a set of elements related to A under the relation R is denoted by equivalence class of A. Subtopic type of relation. Okay, now I'll discuss more subtopic, that is type of relation. We have already discussed that this is our outline: reflexive relation, symmetric relation, and transitive relation. Now we'll discuss some example and we'll give some assignment based on this. Okay, we all already discussed what is a reflexive relation. A be a non-empty set, then a relation R on A is said to be reflexive if A belongs to R for all A belongs to A, that is A related to A for all A belongs to A. Examples. We some give some mathematical example or real life example. We already give the real life example. Now we'll discuss some mathematical example. Relation of parallelism of line on the set of all the straight line is a in a two-dimensional plane. Okay. Suppose there are lots of line here there. We are only selecting parallel line. Okay. Then every line is parallel to itself, so it is reflexive. Okay. Now relation of congruence of triangle on the set of triangle. Only we are considering the relation is relation of congruency. So every triangle is congruent to itself. So relation is reflexive. Relation of greater than equal to on the set of natural number. Suppose x and y are two natural number, and for x and x is greater than equal to x. So every natural number is greater than or equal to itself. So it is reflexive. Similarly, every natural number is less than equal to itself. Every natural number is less than equal to itself. So it is also a every natural number is less than equal to itself. So it is also a is what is that relation? It's also a reflexive relation, friends. Let A equal to 1, 2, 3 be a set and relation R is defined on A as R equal to 1, 1, 2, 2, 3, 3, 1, 3, 2, 1. Okay, now solution. Since 1, 2, 3 belongs to A and 1, 1, 2, 2, 3, 3 belongs to R, so R is reflexive. Because 1, 1, 2, 2, 3, 3 is in R, so R is reflexive. Now, for relation R1 defined on A as R1 equal to 1, 1, 2, 1, 3, 3, 1, 3, 2, 1. Here, since here 1, 2, 3 belongs to A and 1, 1, 3, 3 belongs to R1, but 2, 2 does not belong to R1, hence R1 is not reflexive, friends. Now, relation R on A is said to be non-reflexive if there exists an element A belongs to A such that AA does not belong to R. If at least for one element belongs to A, AA does not belong to R, we say that the relation is not reflexive. Okay. Now, so this is the example of relation which is not reflexive. You can create yourself by considering any set A. Suppose A is ABC. Suppose AA, BP, AD, SC belongs to R. So you can say that this relation is not reflexive because CC is not in R. So you can do yourself. Okay. Now symmetric relation. We are understand all the basic things very neatly. Then we'll go for the question. Symmetric relation. Let A be a non-empty set. then a relation R on A is said to be symmetric. If AB belongs to R, that implies BA belongs to R, where AB belongs to A. So for every AB belongs to R, we have a BA belongs to R, where AB belongs to A. Then we say that the relation is symmetric. That is A related to B. That implies B related to A. We say that for every AB belongs to A, we say that the relation is symmetric. Now we'll discuss some example. Relation of perpendicular of line on the set of all straight line in a two-dimensional plane is symmetric. Suppose there are lots of lines are there. We are collecting those lines which are perpendicular to each other. Here is L, here is M. So L is perpendicular to M, that implies M is perpendicular to L. So AB belongs to A is related to B, that implies B is related to A. So AB belongs to R, that implies BA belongs to R. So this relation is symmetric. Again, relation of congruence of triangles. Suppose this is a triangle, this is another triangle. So if this del 1 is congruent with del 2, then del 2 is also congruent with the del 1. So relation of congruous triangle on the set of triangle is symmetric. If del 1 congruent to del 2, then del 2 also congruent to del 1. So it is symmetric. Okay. Now next class we'll solve this problem, friends. So till then have a nice day. Bye bye, friends. Thank you all.